This video is about linear, time-invariant, or LTI systems. While not all systems are LTI, many are and form an important subset of systems for the purposes of analysis. Furthermore, many real-world phenomena can be modeled by LTI systems, so having useful analytical tools for such systems is very important. In this video, we will look at what it means for a system to be LTI and how to determine if a given system is LTI. A system can generally be represented as a box in a picture with an arrow going in and an arrow going out. The one going in is the input, we'll call it x of n, and the one going out is the output, y of n. And here I'm using discrete time signals, even though this can be generalized for continuous time signals as well. This can also be shown as x of n, creating the output y of n. So the first thing we're going to talk about is linearity. In order for a system to be linear, it has to hold that a superposition of inputs creates the same superposition of the corresponding outputs. Let me illustrate what I mean. Suppose we have an input signal x1 of n, which creates an output y1 of n. And then we have another input x2 of n, and that creates an output y2 of n. And then let's say we have a third signal as an input, x3, which is equal to a scaled version of x1 plus a scaled version of x2, where a1 and a2 are just scalars. This is going to then create an output y3 of n. Now, if the system is linear, then this output y3 is going to be the same combination of the outputs of the individual signals scaled by their corresponding scalars. In other words, this output should be a1 y1 plus a2 y2 if the system is linear. Let's explore what this means with a pictorial example. Suppose that we have our two inputs, x1 and x2, drawn by these examples. So we have discrete values, since it's discrete signals, and let's say that it only exists at the values 0, 1, and 2. This is a function of n, and all of them have an amplitude of 1 for this signal. And let's say that we have another input, x2 of n, which is going to be like this. So this is at -2, -1, and 0, also with an amplitude of 1. And then we're going to say that x1 is going to create an output, which I'm completely making up, y1, that looks like this. So it's got 3 components, and it has an amplitude of 1, 2, and 1. And by the way, when I draw these kind of signals, I'm implying that everything beyond the region where I drew the signal is equal to 0. So the function, or the signal, is defined for all values of n. It's just that they're all 0 outside of the places where I drew them. And x2 is going to bring about y2, which again I'm making up, and it's going to be defined at -1, 0, 1, and 2, with amplitudes of 2 and 1. And of course, zeros beyond. So given these two input signals, that they produce these output signals, what would it mean if the system were linear? So suppose that I'm going to just assign, I'm going to say let a1 equal 2 and A2 equal -1. I'm assigning two scalar values for our multiplication in this top equation over here. And then I want to see what the output is going to be due to the linear combination here of A1x1 plus A2x2. So I'm going to add these two together, the scaled versions of these two signals, and see what they bring about. And if they bring about the same scaling of the corresponding outputs, then the system is linear. So in this case, what I'm going to do is I'm going to assume that the system is linear and show what the output would be. So first, let's look at the signal A1 x1 of n. This is going to be the same thing as we had for x1, except it's going to be at an amplitude of 2. So still at 0, 1, and 2 in n, but now at an amplitude of 2 since we just multiplied every value by A1, which is 2. x2 is going to be scaled by -1, so it's actually going to be facing down. It's going to be A2 times x2 of n, and it's going to be -1, -1, and -1. Add the samples -2, -1, and 0, just like before. Nothing has changed in terms of the locations in n where the function is defined. Nothing got shifted. It only got scaled. And so the corresponding signal, if we add these two together, the actual input signal that we're putting into our system is going to be just the summation of these two, which looks like -1, -1, 1, 2, and 2. Again, I was able to add up these two signals because their value is 0 everywhere outside of where I drew these, so therefore at -2, all I have is this -1 component. At -1 in n, I have this -1 component. Then at 0, I have two components that add up. I have this -1 and a 2 from the first signal, so therefore it becomes an amplitude of 1. And then beyond here, I have this at amplitude 2 and this one at amplitude 2. So therefore these two are at amplitude 2. And this whole signal here is A1 x1 plus A2 x2. So these are the two inputs that we're going to look at and their combination here. And we're going to see what the output would be to this combined signal if the system is in fact linear. So, due to linearity, this system will produce the following outputs. Since we scaled x1 by a1, the output will be the same thing as scaling y1 by a1, and therefore it's just going to be our previous output to this input signal multiplied by 2. So it'll have amplitudes of 2 and 4, and still at the values of -1, 0, and 1. Our next signal here, which is A2, Y2 of n, again, it still exists at the same n values, that hasn't changed, but it's going to be scaled by -1. So therefore it'll be at -2, -2, -1, and -1. And once again, if this is a linear system, then these will add up in the same way that our inputs added up to form a more complicated signal in order to form this final composite signal, which is A1 Y1 of n plus A2 Y2 of n. And again, we can just add up corresponding components here. The component at n equals -1, we have a -2 and a +2, so therefore it adds up to 0 over here. Then we have an amplitude of 2, an amplitude of 1, and an amplitude of -1. and again, it zeros everywhere beyond. So this is amplitude 2, 1, and -1. And that's it. Now, in order to determine if a system is actually linear, because here we made the assumption the system was linear, and then we said that this input, which is a combination of the inputs that are scaled by these A1 and A2 values, if this is the input, it produces this output, which is the same combination and scalings, if the system is linear. But this has to hold for all possible inputs in order for the system to be truly linear. So we showed this pictorially. Now let's look at an example mathematically in order to show whether a given system is linear or not, instead of just assuming that it is and showing what would happen as a consequence. Suppose that we have a system that's going to be defined in the following way. We have, for an input x of n, we get an output y of n, where y of n is going to be defined as the summation from k equals minus infinity up to n of x of k. This is called the accumulator. Basically what it does is it adds up all the values of the input x up to the current value n, which you're analyzing in your output y of n. Now we have another input, whatever it is. Again, this is a mathematical abstraction, x1, which brings about y1, and x2, which causes y2. Now the question is, if we create a linear combination of these two, a superposition, so x3 of n, which is equal to a1 x1, and I'm not specifying these input signals, I'm just writing them mathematically this time instead of drawing them like I did previously, this is going to bring about y3. And the question is this y3 going to be the same combination of these previous outputs, y1 and y2? If it is, then the system is linear. If it's not, then the system is not. So let's try it. So we can write y3 just using the previous definition that we had before as a summation, as the summation from k equals minus infinity up to n of x3, which is this combination of a1 x1 plus a2 x2. And we can further rewrite this as the summation from negative infinity to n of a1 x1 of k plus the summation from k equals minus infinity up to n of a2 times x2 of k. And furthermore, since a1 and a2 are not functions of k, we can bring them out front, and we have a1 times the summation of x1 plus a2 times the summation of x2. So this is our system response to the superposition of x1 and x2, and we called it y3. Well, we can likewise write down y1, which is equal to, again, just using the same definition that we had before, that's equal to the summation of x1 of k, and y2 is equal to the summation of x2 of k. Well, from this we can see that this right here is in fact y1 of n, and this part is y2 of n, and therefore the whole thing equals a1 y1 plus a2 y2. And that's exactly what we expected to get in order for this to be a linear system. So this system is in fact linear. We just proved it by showing that for any arbitrary inputs x1 and x2 and any arbitrary scalings a1 and a2, this property holds. Therefore, the system is linear. If this did not hold, then the system would be nonlinear. The next concept that we want to explore is that of time invariance. Time invariance can be analyzed using the same kind of tools that we just used for linearity in order to prove a given property. In this case, we have that we again have a signal x of n that brings about an output y of n. And now our question is, does a shift in the input bring about the same shift in the output? So mathematically, suppose that we have a given input x1 of n, which brings about y1 of n, and then we have an x2 of n, which is equal to x1 of n minus n0. So we shift everything in x1 by n0, which can be positive or negative or anything. And we ask, well, we know that this brings about y2 of n, which is just whatever output x2 creates. And the question is this equal to y1 of n minus n0? So the same output as we had for x1, except moved by n0, just like our input was moved by that same amount. And once again, we can say that this does in fact hold if this is TI, time invariant. If TI, then this holds. Once again, I'm going to start with a pictorial example, and then we're going to show things mathematically. So first of all, let's say that we have a given input, x1. And like before, it's going to be just these three samples, zeros everywhere outside of that range, all of these at an amplitude of 1. And this is going to create an output, which again I'm making up, and I'm going to use the same one that I had used previously for linearity, and that's going to be defined by this picture with amplitudes of 1, 2, and 1, and of course zeros outside of this range. Now what I'm going to do is I'm going to shift this input signal by a given n0. And I'm going to choose n0 to be positive in this case. It doesn't actually matter, as I said, but just for this particular illustration, I'm going to, so let me actually write it out, that let n0 equal 2. And so we have our signal, which is going to be the same thing as before, except now it just starts at 2. N0 is everywhere outside, still at an amplitude of 1. We have not changed the amplitude at all. It's just a time shift. And now we're going to look at the output, and again, in this case, we're going to say the system is time invariant, and then the output, y of n, basically, if it's equal to the same shift, so therefore we shift everything over by 2, this goes 1, 2, and 3, amplitudes of 1 and 2, and 0 is everywhere else. If this is that same output that we had before, shifted by the same n0, namely 2 in this case, then this system is time invariant. That's what the time invariance property means pictorially. Now, let's look at it as before, mathematically. We'll analyze the same system as we did before. Y of n is equal to the accumulator, so the sum from negative infinity up to n of x k. And we're going to create a signal x1. Again, any signal, and that's going to bring about y1. x2 is going to be x1 shifted by any n0, again not specifying anything, and this brings about the output y2 of n. So let's write out what y2 is equal to. y2 is going to be, again, defined by our system definition. It's going to be the summation of all the x's, but each one of those got shifted by a value n0. So this is what it's going to look like. All the x1s shifted by n0. Let's at the same time take a look at what is y1 shifted by n0, since that's what we expect the output to be equal to if this is a time-invariant system. This is going to be equal to, well, everywhere we had an n, we replace it by n minus n0. The only place we had an n was on top of the summation, the limit of the summation, so that would be the place where we place that, and we have x of k over here. And the question is, are these two things equal? And while it seems like they're not because they have a different form, in fact, with a transformation, we can show that they are. Specifically, we're going to say let a new variable, let's say m, be equal to k minus n0. If we plug that into this equation here, we get that y2 is equal to the summation. We interchange k for m, so m still goes from negative infinity, but now it's going to go to the top limit minus n0. So that is, in fact, n minus n0. And in here, since we let m equal k minus n0, it's just going to be x of m. Well, m is just a variable of summation, so therefore it doesn't matter what it actually is, and just for clarity, let's exchange it back for k. So basically I'm saying let k equal m. And then we get this, which is exactly the same thing as we had here. So we can see that this is in fact equal to y1 of n minus n0, and therefore this system is in fact time invariant. Again, if we had done this analysis and had come up with something that was different between these two, if y2 had not just been y1 of n minus n0, then the system would be not time invariant. Overall, we have seen what it means for a system to be linear and time invariant. We have also seen how to determine if a given system is LTI. Once we know that a system is LTI, we can analyze it readily by using the properties of linearity and time invariance. Specifically, if we know how the system responds to a simple input, then the LTI property means that we know how the system responds to a complicated input if the input is made up of a combination of shifted, scaled versions of the simple input. This is because the LTI property assures that the output will be the same combination of scaling and shifting of the output to the simple signal. We will examine this further in a video about convolution.